look at sugar, there are certain things in the structure that clue me in that sugar is kind of water-like. When I look at this structure, I can see that it'll like water. So sugar is soluble, but it's not infinitely soluble. And what is the solubility? Well, somebody measured it. Let's find it. There it is. So let's say if I had a 250 milliliter cup, 250 milliliters would be a quarter of a liter. This is in grams per liter. I could put 2,000 grams in a liter. Or if I had a cup of coffee, which is about 250 milliliters, I think, that would be 500 grams. I could put 500 grams of sugar in my 250 milliliters. Would you do that? Oh, that would be interesting to see how it tasted. Probably awful. But it should be possible. That's going to be even more because coffee's at a higher temperature, therefore probably can dissolve even more sugar in hot coffee than cold coffee, or room temperature coffee. But but you know, at the 500 grams for a cup, you know, that's plenty soluble. So we just call it soluble. You know, and if we wanted a hard quantitative number, we'd look it up, just like any of these other things. You know, table salt's the other interesting one. We look at the solubility for table salt, 359 grams per liter. And so a cup would be about a quarter. You probably could put 100 grams of table salt into a cup. It should be really, really salty. All right, and table salt is a little different. Table salt is not a molecular compound. You know what we call table salt? Look at the structure. The structure is quite a bit different than sugar, isn't it? Sugar occurs as discrete molecules. Those molecules are quite big in sugar. You know, but table salt does not occur as discrete molecules. So let's just take a look. You know, these sugar molecules are just packed together. This is one unit or one molecule of sugar. There's another view of that. When you pack these together, you can make nice crystals of sugar. When you make nice crystals of sugar, what happens is the sugar molecules are just packed together. Let's look at that really quick here. Sugar crystal, it's different than the lattice structure we saw there earlier. And you can see it here. You know, the molecules are just packed together. There's some dashed lines there, like this. You know, take a box. These molecules are nicely arranged, you know, and therefore you're going to get nice sugar crystals because everything's well ordered. However, these molecules aren't attached to one another. So this is what we call molecular solid. Molecular solids, you know, what's holding these together? You know, not strong bonds. Molecular solids typically have low melting points, easy to break, easy to cut, right? That kind of stuff. But when we look at NaCl, it's got a different structure here. NaCl's got that lattice structure. You know, there's no discrete molecules. All these are bonded to one another. So the bonds just extend out. Everything's tightly held. Therefore, you know, this has a high melting point. Sugar has a low melting point. Sugar is soft. Sodium chloride's hard. These types of things. And unstructured. We don't use, although the solubility rules are kind of similar, we don't use it for Ion compounds, we have to dig a little deeper than that. Do solubility rules, Brian. Let's go there. Next. These solubility rules are going to look similar to the ones in your supplement, but slightly different. I have fewer on here in the supplement, but for ionic compounds, what we do is we first look at the cation. If the cation is group 1 or ammonium, then these are all soluble. It doesn't matter what the anion is. So tell me, what is the formula for ammonium phosphate? Ammonium phosphate. Can you do it in your head? No. Well, what's ammonium? Ammonium is NH4 plus. What is phosphate? PO4 and the charge? PO4 negative 3. So then we got to balance things out. What should we add more of? Ammonium or phosphate? More ammoniums. How many? 3. So altogether we need 3 ammonium. And so ammonium phosphate will be NH4 3 PO4. Does that look right? What should I change? I need parentheses, otherwise I'll have trouble. So I need 3 of the ammoniums and 1 phosphate. Everything's good. Solid ammonium phosphate is a white solid. Will it dissolve in water, or will it not dissolve in water? What do you think, soluble or insoluble? Well, first we look at the cation. If the cation is ammonium attached to anything else, then it is soluble. And so ammonium phosphate is soluble.
I'm sorry, could you repeat why it's soluble again?
It's not why, it just is. I mean, well, right now we're just learning this observation. You know, when you ask why, you know, normally people want to know like a deeper description, like a theoretical kind of description of why it's soluble, like based on some physics. But for us, we're just learning the solubility rules. And so there are different levels of why. Why is it soluble? Because it's part of the rules. Now, rules are going to have more exceptions than laws. And so it's just what's observed. And not always are we going to be correct. But for the most part, we will be. There are some rare exceptions. For example, there's one ionic compound called sodium uranyl acetate, which is a compound with a group 1 cation, sodium. But sodium uranyl acetate is, you predict it's soluble based on this, but it turns out it is insoluble. And so that's one we would have gotten wrong. But for the most part, we'll be okay because things like sodium chloride Sodium chloride is a group 1. Group 1 is the first column, so sodium, potassium, cesium, lithium. Sodium chloride is NaCl, and it is soluble, so we were right. Sodium phosphate is soluble. Sodium silicate is soluble. Sodium carbonate is soluble. You would have been right. Oh, yeah. Potassium carbonate, soluble. Potassium phosphate, soluble. Potassium acetate, soluble. Potassium sulfite, soluble. That's it. And so, why? That's just what's observed. We're taking what's observed and making a little pattern out of it. That's it. But if we want the why, then we have to understand what. You have to come up with some kind of hypothesis. Now, why is something like this soluble, but if I had some other cation, it might not be? Like calcium phosphate. Is calcium phosphate soluble? It turns out calcium phosphate is insoluble. Why? And so it depends. So right now, what we're doing is this. Right now, we're just learning the patterns. Later on, we're going to try to understand them deeper. And so we aren't getting to why, exactly. In chemists, it can be said, why is the ocean blue? And so a lot of people will say, oh, the ocean's blue because of how light is scattered. Red light scattered more than blue light and this and that. But then you go, okay, then why isn't it green? Green light's not as scattered as red light. And so the question about why is a tricky one, because scientists really, all scientists do is describe nature. They're just describing what's observed. That's it. And so they want to describe it in great detail. The reason why, we'll talk about this, but maybe we can figure out some kind of hypothesis after we see some data. And so I have no idea, so let's try to take some more observations and try to figure out what's going on with this. But for right now, we just have these observations. So it's an ammonium salt. Let's do another one. Another example would be sodium arsenate. What do you think about sodium arsenate? What's the formula for sodium arsenate, by the way? Na. AsO4. NaAsO4. Yeah. Yeah, ASO4, the charge is 3, -3. It would be Na3 ASO4 2? Okay, just all right. Actually, it is. It's Na3 ASO4 because of the charges. So this is sodium arsenate. Would you call it trisodium arsenate? No. Well, the tri, all those prefixes we reserve for binary, non-metal compounds, which are called molecular compounds, binary molecular compounds. So this is sodium arsenate. We could figure out that it's trisodium based on the charges. That doesn't mean you don't see it. I mean, have you ever looked at laundry detergent? If you look at laundry detergent, they have trisodium phosphate. And you go, wow. Trisodium phosphate, why didn't they just call it sodium phosphate? A chemist would have called it sodium phosphate. Why didn't they do that? Well, they're figuring, normally you don't want to put the tri if you can figure it out, because it's just wasted space, wasted paper. More trees they have to cut down for that. But for this, the reason why they might have done it here is because there are different ones, depending on if they're talking about, this would be disodium phosphate, or sometimes they call this sodium phosphate dibasic. This would be sodium phosphate monobasic, or monosodium phosphate, something like that. Sometimes they have some weird naming schemes, but anyway, we're just going to stick to ours. This would be sodium arsenate. Is sodium arsenate soluble or insoluble? It's soluble. Why? Well, it depends. Why? It's because it fits our rule. Our rule says that sodium salts are soluble. That's our rule. Sodium, all group 1, sodium, potassium, rubidium, cesium, lithium salts are all soluble. The salts, meaning salts, you know what salts are? Salts are ionic compounds that are not acid. If it's an acid, we call it an acid. If it's not an acid and it's an ionic compound, we call it a salt. Well, anyway, sodium arsenate is soluble. Why? Because that's what the rule says. But is that a really good reason why? No, it's not a good reason. Let's observe. And so it doesn't really explain why. So next, well, what if it's not a group 1 ammonium? If it's not one, if not group 1 or ammonium, then look at the anion. Then look at anion. And so the first anions that we're going to look for are nitrates, chlorates, and acetates. What's the formula for nitrate? NO3. Charge? Not 3 minus. NO3.
2 minus?
Not 2 minus.
Minus.
Just minus. Yeah. NO3 minus. Chlorates? ClO4. Is it 4 oxygenate? Charge? Minus? Is that chlorate? No, that's not chlorate. Actually, try again. Think of ClO 6. ClO 6. Charge? Minus? Unfortunately, that's not chlorate either. Keep guessing, because maybe it hasn't sunk in yet, or look at the periodic table. Maybe I need to put up the periodic table so you can see it. How are you guys memorizing these? Are you just memorizing them like rote memorization, or did you figure out a pattern? Just memorization? That's fine. You can just memorize them. A lot of people use flashcards. You're going to generate a lot of flashcards because not only do you have chlorate, you have perchlorate, chlorite, and hypochlorite. And then you have bromate, perbromate, bromite, and hypobromite. And you have fluorate. It goes on and on. There's a lot. Well, if you're memorizing it, then make sure you work on that memorization because you got to have it down. So chlorate is ClO3. So it doesn't matter to me how do it. You just gotta remember it. ClO3 minus. Acetate. Acetate, you have to do straight memorization. Acetate, what's the formula for acetate? Yeah, C2H3O2 charge? Negative. 232. Actually, that's how I memorized the acetate. 232, 232 minus, 232 minus, CHO. A chlorate, originally when I started memorizing chlorate, all those, I used flashcards. But then when it came to the test, I was trying to write it down and I couldn't remember how many oxygens and what the charge was. So I pretty much threw all my flashcards away and then started writing them over and over again. So I had many 8.5 by 11 sheets of paper, just in the same ion, over and over and over again, writing it. So that's quick. But anyway, if it's one of these, then these are all soluble. And so it doesn't matter what the cation is. Let's take a look at some. Let's look at lead-2 acetate. What's the formula for lead-2 acetate? Mercury 1 is a weird one. Mercury 1's weird, but lead-2 is normal. What's the formula for lead-2 acetate? Lead is Pb. What's the charge on lead-2? What's acetate? Well, we just wrote it over there. 232 minus. So we need how many 2 acetates? We get 2 acetates. They'll nicely balance out the lead, and we're going to form Pb. This would be the formula for lead-2 acetate. So what I want to ask is lead-2 acetate soluble or insoluble?
Yes,
It's soluble. This is soluble. Why? At this point, why is because it's according to our rule for solubility. Hopefully we can see more of a pattern here later on. Don't have to do as much memorization. Let's do iron 3 nitrate, aka ferric nitrate. What's the formula for iron 3 nitrate or ferric nitrate? Fe, NO3, 3. That's it. That's right. Is it soluble or insoluble? It's soluble. What is this one called? What is that called? It's a white solid. Is this called silver nitrate or silver 1 nitrate? This is just called silver nitrate because silver is a fixed charge, +1, so silver nitrate. Is silver nitrate soluble or insoluble? It's soluble. Okay, what if it's not one of these? Then we've got to look at another series of anions. So we'll go on to C here. If it's not one of these, then we look for chloride, bromide, and iodide. Well, there's one important member of this family missing. Which one is it? Yeah, fluoride is missing. What about fluoride? Fluoride is intentionally left out. Fluoride is left out. The reason is because it's more complex. Exceptions. Let me talk about what the exceptions are. And so chlorides, what's the formula for chloride? Bromide and iodide ions. These are soluble except when paired with silver. What's this called? Hg2 2+. This is the weird one. This is called mercury 1 or mercury 2? Mercury 1 or mercury 2? Mercury 1. This is mercury 1, and you have to take it as a unit. You can't have half of this. You have to take the whole thing. So silver, mercury 1, lead 2. If we included fluoride in there, then there are many more that we have to add to this. And those would be valid for fluoride, but not valid for everything else. So the best way is fluoride is left out because of its many exceptions. Best to look up solubility individually. For fluoride. So, for example, if I'm looking at nickel 2 fluoride, if I'm looking at nickel 2 fluoride, I think it's soluble because it's not one of the exceptions. Let's take a look here. Here's nickel 2 fluoride, the lattice type structure. Well, maybe it's okay. It's pretty soluble, 4 grams per 100 milliliters. And so that would have worked. But if I go to other nickel compounds, I'm going to have other problems. And so nickel has many more exceptions. We don't really do it. Not nickel, fluoride. Fluoride does. So let's take a look at these. And the chlorides fluorides I'd look up individually. Chlorides, bromides, and iodides, I just use this. And so one example would be this, PbCl4. What's PbCl4 called? PbCl4 is called lead 4 chloride. Is lead 4 chloride soluble or insoluble? It's soluble. Yeah, it's weird. This is soluble. Oddly enough, this one, PbCl2, which is called, what's this called? This is called lead 2 chloride. This is insoluble. Why is that? Yeah, why that is something we really want to know, but do we really know it? No, not yet. We have to look at more. Maybe we can see some kind of pattern. Maybe we can hypothesize something. But it has to do with the structure. Oddly enough, I'll just tell you, lead 2 chloride forms a lattice type structure. Lead 4 chloride forms molecules, not a lattice type structure. And so these are quite different in terms of properties. So this is more like a molecular, this is more like a salt, a regular salt. There's quite a big difference in properties. And then the question is, why is that then? Why does lead 4 chloride form molecules? And lead 2 chloride form lattice? Well, it has to do with the bonding. Bonding is what we call much more covalent. We'll talk about this later, but the bonding is much more covalent versus ionic. And you go, why is it more covalent than lead 4 chloride? Well, then it has to do with, and so we want to dig into it deeper and deeper so we can get a more descriptive picture of what's going on, basically. But for right now, we're just looking at these factual observations here, patterns. Let's take a look at silver chloride. What's the formula for silver chloride? It's a nice white solid. Nickel 2 salts are green like this. Really nice. What's the formula for silver chloride? AgCl. Is AgCl soluble or insoluble? Insoluble. And so we saw AgCl before. An insoluble. If an insoluble solid is formed in a chemical reaction, we call it precipitation. And so it's important to know because these precipitates are quite stable. The ions like each other. They like each other enough that they can form a solid and precipitate. All right, we're going to keep moving here to the next thing. Let's see. D. Okay, the next series of anions to look at are the sulfates. What is sulfate? Sulfate is SO4 2 minus. That's right. It's SO4 2 minus. Good. Did you do that from memory, or did you look it up? Memory. Or you could look at. Have it written down before. Memory would just be from the pattern too, so it would be from memory. So sulfates are soluble, except for when they're paired with silver, lead, mercury, calcium, strontium, and barium. Silver should have a little asterisk here. But sulfates are soluble except when paired with silver ion, lead 2, mercury 1, mercury 2, calcium, strontium, barium. So let's look at some examples here. Let's look at iron 3 sulfate. Iron 3 sulfate. What's the formula for iron 3 sulfate? FeSO4 3. FeSO4 3. Close, but Fe2. Fe2SO4 3. Basically, we need 2 of these iron 3 pluses, which gives us a total of 6 plus, and 3 of these 2 minus sulfates, which gives us 6 minus. So plus 6 totals, minus 6 total gives us Fe2SO4 3. Iron 3 sulfate, is it soluble or insoluble? Yeah. Iron 3 sulfate should be soluble. How about this one? What would you call this? BaSO4. Would that be called barium 2 sulfate? Barium 2 sulfate? Or just barium sulfate? Yeah, just barium sulfate. Barium is a fixed charge, it's group 2, so this is barium sulfate. Is barium sulfate soluble or insoluble? Barium sulfate turns out to be insoluble. It's a bit odd, but it's insoluble. All right, we're going to stop here. We'll take a break and then start again.